Imagine you're lying in bed, the world around you quiet and still, and your thoughts begin to drift. Out there, beyond what we see and know, the universe holds questions that not even the greatest minds can fully answer. These are the kinds of puzzles that don't just keep you awake, they keep scientists up at night, too. In this gentle journey, we'll explore the paradoxes that stir the edges of science and philosophy, where reality bends and the answers remain just out of reach. So get cozy, let your mind wander freely, and if you enjoy drifting through these mysteries with me, don't forget to subscribe for more slow, thoughtful stories like this one. The Fermi paradox is one of the most compelling and unsettling questions in astrobiology and cosmology, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" The paradox highlights the contradiction between the high probability of extraterrestrial civilizations existing in the universe and the complete lack of evidence for such civilizations. Given the vast number of stars in the Milky Way, estimated at 100 to 400 billion, and the even greater number of galaxies in the observable universe, it seems statistically likely that life, even intelligent life, should have arisen elsewhere. Yet despite decades of searching through radio telescopes, optical surveys, and other detection methods, humanity has found no definitive signs of alien civilizations. This silence raises profound questions about the nature of life, intelligence, and the universe itself. The foundation of the Fermi paradox lies in the Drake equation, formulated by astronomer Frank Drake in 1961. This equation attempts to estimate the number of active communicative extraterrestrial civilizations in the Milky Way by considering factors such as the rate of star formation, the fraction of stars with planets, the number of habitable planets per system, the likelihood of life emerging, the probability of intelligence developing, and the lifespan of a technological civilization. While the equation is not a definitive calculation, many of its variables remain unknown. It provides a framework for thinking about the likelihood of alien life. Even conservative estimates suggest that there should be at least a few civilizations capable of interstellar communication within our galaxy. Yet, the silence persists. One possible explanation for the Fermi paradox is that intelligent life is exceedingly rare. While microbial life may be common in the universe, the emergence of complex, intelligent life might require an improbable series of evolutionary steps. Earth's history shows that life appeared relatively quickly after the planet's formation, but it took billions of years for multicellular organisms to evolve and only a few million for humans to develop technology. The Great Filter hypothesis suggests that there may be one or more insurmountable barriers preventing life from reaching an advanced stage. This filter could lie in the past perhaps. The emergence of life itself is astronomically unlikelier in the future, implying that advanced civilizations inevitably destroy themselves through war, environmental collapse, or other catastrophes. If the Great Filter is behind us, humanity is extraordinarily fortunate. If it lies ahead, our future may be bleak. Another possibility is that intelligent civilizations are short-lived. Technological advancement might bring with it existential risks that few civilizations survive. Nuclear war, climate change, artificial intelligence, or bioengineered pandemics could wipe out civilizations shortly after they develop the capacity for interstellar communication. This would explain why we detect no signals. Civilizations simply do not last long enough to make their presence known. The fact that humanity has only been broadcasting radio waves for about a centuria blink of an eye on cosmic timescales suggests that technological civilizations might be ephemeral. If most civilizations last only a few centuries before collapsing, the chances of overlapping with another are slim. Alternatively, advanced civilizations might be deliberately avoiding contact. The zoo hypothesis proposes that extraterrestrial societies are aware of Earth but choose not to interfere, perhaps to allow humanity to develop naturally or to avoid cultural contamination. This idea draws parallels to how scientists study uncontacted tribes in remote areas, observing without interfering. Another variation is the dark forest hypothesis, which posits that the universe is a dangerous place, and civilizations hide to avoid attracting the attention of potentially hostile others. In this scenario, broadcasting our existence could be a grave mistake. These theories, while speculative, suggest that the absence of contact might be a deliberate strategy rather than evidence of absence. It is also possible that we are simply too early to the cosmic party. The universe is 13.8 billion years old, but Earth is only 4.5 billion years old. The first stars formed hundreds of millions of years after the Big Bang, but they were composed almost entirely of hydrogen and helium, lacking the heavier elements necessary for life. It took several generations of stars to produce the carbon, oxygen, and other elements that make up planets and living organisms. If intelligent life tends to emerge much later in the universe's timeline, humanity might be among the first civilizations to arise. In this case, the silence could be because other civilizations have not yet had time to develop or spread across the galaxy. Technological limitations might also play a role in our inability to detect extraterrestrial life. Our current methods of searching for aliens, primarily radio telescopes and optical surveys, are limited in scope and sensitivity. Advanced civilizations might use communication methods we cannot yet detect, such as neutrino signaling or quantum entanglement. Interstellar travel, while theoretically possible, may be so difficult and energy-intensive that civilizations rarely attempt it. Even if alien probes or spacecraft have visited our solar system, they might be too small or advanced for us to recognize. The vast distances between stars, combined with the limitations imposed by the speed of light, could make interstellar communication and travel impractical, trapping civilizations in isolation. Another consideration is that life might exist in forms we do not recognize. Our search for extraterrestrial life is biased toward conditions similar to Earth's, but life elsewhere could be radically different. Silicon-based life, non-carbon-based biochemistry, or even digital intelligences might thrive in environments we consider inhospitable. If alien life does not conform to our expectations, we might overlook it entirely. Similarly, advanced civilizations might have transitioned to post-biological forms, existing as artificial intelligences or distributed networks that do not emit detectable signals. The universe could be teeming with life, but in forms so alien that we fail to perceive them. The Fermi paradox forces us to confront the possibility that we are alone. While this idea is unsettling, it is not implausible. The chain of events that led to human existence, the precise tuning of physical constants, the stability of our solar system, the series of evolutionary accidents that produced intelligence, might be so improbable that Earth is unique. This perspective, known as the rare Earth hypothesis, argues that the conditions necessary for complex life are so specific that they are unlikely to be replicated elsewhere. If true, humanity is not just alone in the Milky Way, but possibly in the entire observable universe. Despite the lack of evidence, the search for extraterrestrial intelligence continues. Projects like SETI, Search for Extraterrestrial Intelligence, and Breakthrough Listen scan the skies for artificial signals, while missions to Mars and the icy moons of Jupiter and Saturn seek signs of microbial life. The discovery of even simple extraterrestrial life would have profound implications, suggesting that life is not a fluke but a common phenomenon. If intelligent life is found, it would revolutionize our understanding of our place in the cosmos. Until then, the Fermi paradox remains an open question, a humbling reminder of how little we know about the universe and our role within it. The silence of the cosmos is either a profound mystery or a sobering truth. It challenges our assumptions about life, intelligence, and the inevitability of progress. Whether the answer lies in the rarity of life, the fragility of civilizations, or the limitations of our own perception, the Fermi paradox underscores the uniqueness of our existence. In a universe that seems tailor-made for life, the absence of others may be the most significant clue of all. The black hole information paradox is one of the most profound and unresolved problems in modern physics. exposing a deep tension between quantum mechanics and general relativity, the two most successful theories describing the universe. At its core, the paradox arises from a fundamental contradiction. Quantum mechanics insists that information about the state of a physical system can never be lost, while general relativity predicts that black holes irreversibly destroy anything that falls into them, including the information they carry. This clash not only challenges our understanding of black holes, but also hints at a missing link in our comprehension of space, time, and the very fabric of reality. Quantum mechanics, the framework governing the behavior of particles at microscopic scales, is built on the principle of unitarity, the idea that the evolution of a quantum system is always reversible. In other words, if you know the complete quantum state of a system at any given time, you can, in theory, reconstruct its past and predict its future. This implies that information, whether it's the position of an electron or the spin of a photon, can never truly vanish. Even if a system becomes scrambled or entangled, the information is preserved in some form. This principle has been tested and confirmed in countless experiments, from particle collisions to quantum computing. General relativity, on the other hand, describes gravity as the curvature of space-time caused by mass and energy. Black holes, one of the most extreme predictions of this theory, are regions where space-time is so warped that nothing, not even light, can escape once it crosses the event horizon. According to classical general relativity, anything that falls into a black hole is lost forever, crushed into the singularity at its center. This includes not just matter and energy, but also the information they carry, a direct violation of quantum mechanics' no-hiding theorem. The paradox was sharpened in the 1970s when Stephen Hawking applied quantum field theory to black holes and discovered that they are not completely black. Due to quantum fluctuations near the event horizon, black holes emit radiation now known as Hawking radiation and slowly lose mass over time. This process implies that a black hole will eventually evaporate entirely, leaving behind only thermal radiation. But here lies the crux of the problem. Hawking radiation appears to be purely random, carrying no information about what fell into the black hole. If the black hole vanishes, so does all the information it ever consumed, violating quantum mechanics' demand for information preservation. This contradiction sent shockwaves through theoretical physics. If Hawking was correct, then quantum mechanics, a theory that has been experimentally verified to astonishing precision, must be incomplete or wrong when applied to black holes. Alternatively, general relativity might need modification at the quantum level. Resolving this paradox is not just an academic exercise. It could be the key to unlocking a theory of quantum gravity, a unified framework that reconciles the two pillars of modern physics. Several potential solutions have been proposed over the years, each with its own implications and challenges. One early idea was that the information is indeed lost and quantum mechanics must be revised. This was Hawking's original stance, but it was met with strong opposition, particularly from physicists like Leonard Susskind and Gerard Hooft, who argued that abandoning unitarity would undermine the entire foundation of quantum theory. Instead, they proposed that the information is somehow encoded in the Hawking radiation, though the mechanism was unclear at the time. This led to the development of the holographic principle, inspired by earlier work on black hole thermodynamics. The principle suggests that all the information contained within a volume of space can be represented as a theory living on its boundary, much like a hologram, where a 2D surface encodes a 3D image. In the case of a black hole, the information about everything inside it might be imprinted on its event horizon in the form of microscopic quantum states. As the black hole evaporates, this information could be gradually released in the Hawking radiation, preserving unitarity. This idea gained further support from string theory, particularly through the ADS-CFT correspondence, which provides a concrete example of how a higher dimensional gravitational theory can be equivalent to a lower dimensional quantum field theory. Another proposed resolution is the idea of black hole remnantstony, stable remnants left behind after Hawking evaporation that contain all the missing information. However, this raises new problems, such as the necessity for an infinite number of remnant states to encode all possible information, which seems physically implausible. A more radical suggestion is that black holes don't actually have event horizons in the traditional sense. The firewall hypothesis, proposed by physicists Ahmed Almheri, Donald Maroff, Joe Polchinski, and James Sully, argues that an infalling observer would encounter a searing wall of high-energy particles at the horizon, rather than smoothly passing through. This would prevent information from being lost inside the black hole, but contradicts the equivalence principle of general relativity, which states that free-falling observers should experience no extreme effects at the horizon. Recent advances in quantum gravity, particularly in the study of quantum entanglement and wormholes, have provided new insights. The eerie conjecture, proposed by Juan Maldacena and Leonard Susskind, suggests that entangled particles might be connected by microscopic wormholes, implying that spacetime itself could emerge from quantum entanglement. If true, this could mean that information falling into a black hole remains entangled with the Hawking radiation outside, effectively preserving it without violating any physical laws. Despite these theoretical developments, the paradox remains unresolved. Experimental verification is nearly impossible with current technology, as observing Hawking radiation directly from astrophysical black holes is beyond our capabilities. However, analog black hole systems in condensed matter physics that mimic black hole behavior have been used to test some aspects of the paradox in the lab. The black hole information paradox is more than just a puzzle about black holes. It is a gateway to deeper questions about the nature of reality. Solving it may require a complete overhaul of our understanding of spacetime, information, and quantum mechanics itself. Whether the answer lies in holography, wormholes, or some yet undiscovered principle, the resolution will undoubtedly reshape physics in ways we can scarcely imagine. Until then, the paradox stands as a stark reminder of how much we still don't know about the universe. At the heart of Einstein's theory of special relativity lies a mind-bending phenomenon. Time itself is not absolute, but flows differently depending on how fast one is moving. The twin paradox is one of the most striking illustrations of this principle. Imagine two identical twin zones stays on Earth, while the other embarks on a high-speed journey through space at a significant fraction of the speed of light. Upon returning, the traveling twin finds that they have aged less than their Earth-bound sibling. This is not science fiction, but a direct consequence of relativistic physics, confirmed by experiments and deeply embedded in the mathematical framework of modern physics. The paradox arises from the fact that, according to special relativity, time dilation occurs when two observers move relative to each other at constant velocity. Each twin sees the other's clock running slower due to their relative motion. If motion were truly symmetric, one might expect each twin to perceive the other as younger, leading to a logical contradiction when they reunite. However, the paradox is resolved because the situation is not perfectly symmetrical. The traveling twin must accelerate to turn around and return to Earth, breaking the inertial frame symmetry assumed in simple time dilation scenarios. Einstein's 1905 theory of special relativity rests on two foundational postulates. The laws of physics are the same in all inertial frames, frames moving at constant velocity, and the speed of light in a vacuum is constant for all observers, regardless of their motion. From these principles, it follows that space and time are interwoven into a single continuum spacetime, and that measurements of time and distance are observer-dependent. The Lorentz transformation equations mathematically describe how time intervals and lengths change between different inertial frames. Crucially, time dilation means that a moving clock ticks slower than one at rest from the perspective of a stationary observer. The twin paradox was first articulated shortly after Einstein introduced special relativity, and it has since been tested and verified in numerous ways. One of the earliest confirmations came from observations of cosmic ray muon sunstable particles created in the upper atmosphere. These particles decay so quickly that, at rest, they should vanish before reaching the Earth's surface. Yet, they are detected in abundance because their high velocity, close to the speed of light, causes time to dilate from our perspective, extending their lifespan. Similarly, atomic clocks flown on airplanes or satellites have been shown to tick at slightly different rates compared to those on the ground, matching relativistic predictions. The asymmetry in the twin paradox comes from the fact that the traveling twin does not remain in a single inertial frame. To leave Earth, reach a distant star, and return, they must accelerate, changing direction and velocity. General relativity, which incorporates acceleration and gravity, further refines the explanation, but the core resolution lies in special relativity's treatment of non-inertial motion. The Earth-bound twin remains in a single inertial frame, approximately, ignoring Earth's rotation and orbit, while the traveling twin's journey involves at least 3 phases: outward acceleration, deceleration and turnaround, and return acceleration. During these changes in velocity, the traveling twin experiences a shift in their proper time relative to the stationary twin. Mathematically, the proper time experienced by each twin can be calculated using the space-time interval, which remains invariant in all reference frames. For the Earth twin, time passes at the usual rate, while for the traveling twin, the elapsed time is shorter due to their high velocity. The exact difference depends on the speed and duration of the journey. For example, if one twin travels to a star 4 light-years away at 80% the speed of light, the round trip would take 10 years from Earth's perspective. But due to time dilation, the traveler would experience only 6 years. The faster the journey, the more extreme the effect approaching the speed of light. The traveler's subjective time could be arbitrarily small compared to Earth's. A common misconception is that the paradox can be explained purely by the Doppler effect, the shift in observed frequency due to relative motion. While the Doppler effect does play a role in how each twin perceives the other's clock during the journey, it does not account for the cumulative time difference upon reunion. The key is that the traveling twin's path through space-time is objectively shorter, in terms of proper time, due to their motion, a geometric property of Minkowski spacetime. Some have questioned whether the paradox could be avoided if the traveling twin never turned around, instead coasting indefinitely away from Earth. In that case, each twin would indeed see the other as aging more slowly, but they would never reunite to compare clocks, making the paradox moot. The act of returning, and thus accelerating, is what breaks the symmetry and allows for an absolute difference in aging. The twin paradox has profound implications beyond a mere curiosity of relativity. It demonstrates that time is not a universal constant, but a flexible dimension shaped by motion. GPS satellites must account for both special relativistic time dilation, due to their orbital speed, and general relativistic time dilation, due to Earth's gravity, to maintain accuracy. Without these corrections, GPS positioning would drift by kilometers within days. Philosophically, the paradox challenges our intuitive notions of time. We are accustomed to thinking of it as an unchanging backdrop against which events unfold, but relativity shows that time is dynamic, interwoven with space, and experienced differently depending on one's state of motion. The twin paradox is not just a thought experiment, it is a real, measurable effect that forces us to abandon Newtonian absolutes and embrace a universe where time itself is relative. In the decades since Einstein's revolution, no experiment has contradicted special relativity's predictions. Particle accelerators routinely accelerate particles to near-light speeds, observing time dilation in their decay rates. Future interstellar travel, should it ever become feasible, would have to contend with these relativistic effects. A crew traveling to even the nearest stars at relativistic speeds would return to an Earth that had aged decades or centuries more than they had. The twin paradox remains one of the most elegant demonstrations of relativity's strangeness. It shows that time is not just something we measure with clocks, but a dimension as malleable as space, bending to the dictates of motion. In doing so, it reshapes our understanding of reality itself. The grandfather paradox is one of the most famous thought experiments in discussions of time travel, exposing the logical inconsistencies that arise if backward time travel were possible. The scenario is simple yet devastating. If a person travels back in time and kills their own grandfather before their parent is conceived, then the time traveler would never be born, which means they could never have gone back to commit the act in the first place. This paradox strikes at the heart of causality, the fundamental principle that cause must precede effect. If time travel to the past were possible, it would seemingly allow effects to precede their causes, creating loops that defy classical logic. The paradox was first articulated in the early 20th century as science fiction writers and physicists began exploring the implications of Einstein's theory of relativity, which allows for the theoretical possibility of time dilation and even closed time-like curve paths through space-time that could loop back on themselves. Unlike the twin paradox, which is a real, experimentally verified consequence of special relativity, the grandfather paradox remains a hypothetical problem because time travel to the past is not known to be physically possible. However, it serves as a critical tool for examining the logical structure of time and the potential consequences of bending or breaking it. One proposed resolution comes from the idea of self-consistency, championed by physicist Igor Novikov in the 1980s. The Novikov self-consistency principle asserts that any actions taken by a time traveler were always part of history, meaning that any attempt to change the past would inherently fail because the timeline must remain consistent. In this view, if you traveled back to kill your grandfather, some unforeseen event, a gun jamming, a sudden change of heart, or an intervening bystander would prevent the act from succeeding. The past is immutable, and any appearance of free will in altering it is an illusion. This idea aligns with the concept of a block universe in relativity, where past, present, and future coexist in a fixed four-dimensional space-time structure. Another potential solution arises from the many worlds interpretation of quantum mechanics, which suggests that every possible outcome of a quantum event spawns a new, branching universe. Applied to time travel, this would mean that any attempt to change the past doesn't alter the original timeline, but instead creates a new, divergent reality. In this scenario, killing your grandfather wouldn't erase you from existence. It would simply strand you in a parallel universe where your grandfather died young and your alternate self was never born. Your original timeline remains untouched, preserving causality at the cost of infinite branching realities. This interpretation avoids the paradox by making time travel an act of universe hopping rather than true past alteration. A more radical solution comes from the study of closed time-like curves, CTCs, theoretical constructs in general relativity that allow for paths looping back in time. Some solutions to Einstein's equations, such as those involving wormholes or rotating cosmic strings, permit CTCs under specific conditions. Quantum mechanics introduces another layer, the concept of post-selection, where only self-consistent timelines are allowed to exist. Physicists like David Deutsch have proposed that quantum mechanics could enforce consistency in CTCs, meaning any paradoxical actions would cancel themselves out probabilistically. In this model, the universe acts like a self-correcting system where only non-paradoxical events can occur within time loops. Despite these theoretical workarounds, the grandfather paradox remains unresolved because we lack empirical evidence for time travel or the existence of alternate timelines. Experiments in quantum mechanics have shown that particles can exhibit retrocausality, where future events appear to influence past ones, but this is a far cry from macroscopic time travel. The paradox forces us to confront deep questions about free will, determinism, and the nature of existence. If the past cannot be changed, does that mean our futures are predetermined? If multiple timelines exist, what does that say about the uniqueness of our reality? Philosophically, the paradox challenges our intuitive sense of time as a linear, one-way progression. It exposes the fragility of cause and effect when temporal order is disrupted. Some physicists argue that the very existence of such paradoxes implies that backward time travel is fundamentally impossible, a cosmic safeguard against logical inconsistencies. Others see it as proof that our understanding of physics is incomplete, requiring a deeper theory that unites quantum mechanics and general relativity. Until time travel is either proven or conclusively ruled out, the grandfather paradox will remain a captivating puzzle that blurs the line between science fiction and theoretical physics, while reminding us that time, in all its mystery, may be far stranger than we imagine. At the heart of quantum mechanics lies a profound and unsettling mystery: the measurement problem. This fundamental issue arises from the strange behavior of quantum systems, where particles exist in superpositions, multiple states simultaneous, until a measurement forces them to choose a single outcome. The act of observation appears to collapse the wave function, the mathematical description of a quantum system, from a spread-out probability distribution into a definite state. But what exactly constitutes a measurement? Why does observation have this effect? And does consciousness play a role in shaping reality? These questions have puzzled physicists since the early 20th century and remain unresolved, giving rise to competing interpretations that challenge our understanding of reality itself. The problem originates in the mathematical formalism of quantum mechanics. A quantum system, such as an electron, is described by a wave function, π3, xion, which encodes all possible states the system can occupy. For example, in the famous double-slit experiment, an electron passes through two slits simultaneously, interfering with itself as if it were a wave. This interference pattern demonstrates that the electron exists in a superposition of positions. It is not localized to one slit or the other. However, when scientists place a detector to observe which slit the electron goes through, the interference pattern disappears. The electron behaves like a particle, passing through one slit definitively. Somehow, the act of measurement destroys the superposition. This phenomenon raises deep questions. Why does the wave function collapse upon measurement? What qualifies as a measurement? Does it require a conscious observer, or is any interaction with a macroscopic system sufficient? The Copenhagen interpretation, formulated by Niels Bohr and Werner Heisenberg, offers one answer. It posits that quantum systems remain in superpositions until they interact with a classical measuring device, at which point the wave function collapses probabilistically. In this view, the observer does not need to be conscious. Any irreversible interaction that records the outcome is enough. However, the Copenhagen interpretation is vague about the exact boundary between quantum and classical systems, leading to criticisms that it sidesteps the core issue. An alternative perspective is the many worlds interpretation, MWI, proposed by Hugh Everett in 1957. MWI rejects wave function collapse entirely, suggesting instead that every possible outcome of a quantum measurement becomes real in a branching multiverse. When an electron is measured, the universe splits. In one branch, the electron is detected at one slit. In another, it is detected at the other. This eliminates the need for an external observer to collapse the wave function, but at the cost of an ever-proliferating number of parallel realities. While MWI is mathematically elegant, it treats the entire universe as a single quantum system. It is philosophically jarring, as it implies the existence of countless unobservable worlds. Another approach is quantum decoherence, which explains the apparent collapse of the wave function through interactions with the environment. When a quantum system interacts with its surroundings, such as air molecules, photons, or a measuring device, its superposition becomes leaked into the environment, making the system behave classically for all practical purposes. Decoherence does not solve the measurement problem outright. It still doesn't explain why one outcome is observed over another, but it bridges the gap between quantum weirdness and the familiar classical world. Experiments with large molecules and even tiny mechanical oscillators have demonstrated decoherence in action, showing how fragile superpositions are in the presence of disturbances. More radical interpretations push the boundaries of physics and philosophy. The von Neumann-Wigner interpretation suggests that consciousness itself causes wave function collapse, implying a deep link between mind and matter. While this idea is largely marginalized in mainstream physics, it resurfaces in discussions about the role of observers in quantum experiments. On the other hand, objective collapse theories, such as the Gherardi-Rimini-Weber (GRW) model, propose that wave functions collapse spontaneously at random intervals, with probabilities scaled by the size of the system. These theories introduce small, non-linear modifications to quantum mechanics, offering testable predictions, though no definitive evidence has been found yet. The measurement problem is not just philosophical, it has practical implications for quantum technologies. Quantum computers rely on maintaining superpositions, qubits, long enough to perform calculations. Understanding decoherence is crucial for error correction. Similarly, quantum cryptography exploits the fact that measuring a quantum system disturbs it, enabling secure communication. Resolving the measurement problem could unlock even deeper control over quantum systems, potentially revolutionizing computing, sensing, and fundamental physics. Despite nearly a century of debate, no consensus has been reached. The Copenhagen interpretation remains the most widely taught, but its ambiguities frustrate many. MWI appeals to those who prefer a deterministic, collapse-free universe, but its existential implications are hard to swallow. Decoherence provides a partial explanation, but leaves the core mystery intact. The measurement problem forces us to confront the limits of our knowledge. Is reality truly probabilistic at its core? Are there hidden variables we haven't discovered? Or is our notion of reality itself incomplete? Until new experiments, perhaps involving larger quantum systems or tests of collapse theory, shed light on these questions, the measurement problem will endure as one of the most profound puzzles in science. It challenges not only our understanding of the physical world, but also our place within it, blurring the line between observer and observed, and leaving us to wonder what really happens when we look. In the vast expanse of cosmic time and space, a disturbing possibility emerges from the laws of thermodynamics. What if everything we perceive as reality, the stars, galaxies, history, even our own memories, is nothing more than a fleeting hallucination of a single, spontaneously formed conscious mind? This is the essence of the Boltzmann Brain paradox, a thought experiment so unsettling that it challenges not just our understanding of the universe, but the very foundations of scientific reasoning itself. The paradox traces its origins to 19th century physicist Ludwig Boltzmann, who grappled with the relationship between entropy and the arrow of time. Entropy, a measure of disorder in a system, always increases in closed systems according to the second law of thermodynamics. Yet our observable universe appears remarkably ordered, with complex structures like galaxies, planets, and life itself. Boltzmann proposed a radical solution. Perhaps our low-entropy universe is simply a rare statistical fluctuation within a much larger high-entropy cosmos. In an infinite or near-infinite universe, even the most improbable states, including an ordered universe like ours, must occasionally arise by random chance. But this explanation leads to an even stranger consequence. If complex structures can emerge from random fluctuations, then statistically, it is vastly more probable for a single, self-aware brain complete with false memories of a coherent universe to spontaneously form than for an entire ordered cosmos to emerge. A Boltzmann brain would be a momentary configuration of particles that, by sheer accident, arranges itself into a conscious state, complete with the illusion of a past and surroundings. The implications are existential. If Boltzmann brains are more likely than real, evolved observers like ourselves, then we have no way to trust that our perceptions reflect an objective, persistent reality. The paradox gains traction when considering modern cosmology. Current evidence suggests our universe is headed toward a heat death, a state of maximum entropy where all energy is evenly distributed and no meaningful work can be done. In such a scenario, fluctuations could theoretically produce Boltzmann brains in the far future, long after all stars have burned out. But the problem runs deeper. If the universe is infinite or part of a multiverse, then these disembodied observers should vastly outnumber real observers like us. The fact that we don't perceive ourselves as Boltzmann brain-isolated minds floating in a void suggests something is wrong with this picture. Physicists have proposed several ways to resolve the paradox. One approach is to reject the idea that our universe is a fluctuation altogether. Inflationary cosmology, which describes the rapid expansion of the early universe, provides an alternative explanation for our low-entropy initial conditions. If inflation set the universe into a highly ordered state naturally, then no statistical fluke is needed, and Boltzmann brains become unnecessary. However, this relies on inflation being a complete theory, which is still an area of active research. Another solution comes from quantum mechanics. In some interpretations, conscious observers play a role in collapsing quantum states into reality. If consciousness is fundamental rather than emergent, then the probability of a Boltzmann brain forming might be effectively zero, as it would require not just the right particle arrangement, but also a genuine act of observation. However, this ventures into speculative territory, merging the measurement problem with cosmology in ways that remain controversial. A more pragmatic response is to treat the Boltzmann brain paradox as a reductio ad absurdum, sign that our current cosmological models are missing something critical. For instance, if the universe is not eternal, but has a finite lifespan, or if entropy behaves differently on cosmological scales than we currently understand, the paradox might dissolve. Some theories of quantum gravity or dark energy could eventually provide mechanisms that prevent Boltzmann brains from dominating the statistics of observers. The paradox also raises profound philosophical questions about the nature of consciousness and reality. If we cannot rule out the possibility that we are Boltzmann brains, then the reliability of memory, perception, and even scientific inference is called into question. Science assumes that the universe operates consistently over time and that our observations reflect an objective reality. But if most observers in the cosmos are fleeting illusions, this assumption crumbles. The very act of doing science building on past experiments, trusting our instruments, and extrapolating laws of physics becomes suspect. Despite its bizarre premise, the Boltzmann brain paradox serves a valuable purpose. It exposes gaps in our understanding of entropy, cosmology, and the nature of existence. It forces physicists to confront the assumptions underlying theories of the universe's origin and fate. Whether through refined models of inflation, a deeper theory of quantum gravity, or a revolutionary rethink of consciousness itself, resolving the paradox may lead to breakthroughs in how we see reality. For now, the paradox stands as a humbling reminder of how little we truly know. In an infinite cosmos governed by probability, the line between reality and illusion may be thinner than we dare imagine. The universe we perceive may be stable and ordered, or it may be a flicker in the dark, a momentary thought in the mind of a brain that, by the laws of physics, shouldn't exist at all. In the world of statistics, few phenomena are as counterintuitive and as potentially misleading as Simpson's paradox. Named after British statistician Edward H. Simpson, who formalized it in 1951, though it was observed as early as 1899 by Carl Pearson. This paradox occurs when a trend appears in different groups of data, but disappears or reverses when those groups are combined. At its core, it reveals how naive aggregation of data can lead to entirely wrong conclusions, with serious implications for fields ranging from medicine to economics to artificial intelligence. The classic example comes from a 1973 study of gender bias in graduate admissions at the University of California, Berkeley. When looking at overall admission rates, men appeared to have a higher acceptance rate than women, suggesting possible discrimination. However, when the data was broken down by individual departments, the trend reversed. Most departments actually showed a slight bias in favor of women. The paradox arose because women tended to apply to more competitive departments with lower overall admission rates, while men disproportionately applied to less selective departments. The aggregate data told one story, the disaggregated data told another. Mathematically, Simpson's paradox occurs because of what statisticians call lurking variables, or confounding factors, hidden influences that distort the relationship between the variables being studied. In the Berkeley case, the choice of department was the lurking variable that altered the interpretation of the gender admission relationship. The paradox can be expressed through contingency tables, where the direction of association between two variables changes when a third variable is introduced. Formally, it violates the principle that marginal associations should be consistent with partial associations, demonstrating that statistical relationships are not always transitive. One of the most striking real-world consequences of Simpson's paradox appears in medical research. Consider a hypothetical study comparing the survival rates of two treatments for kidney stones. When examining small and large stones separately, treatment A might have higher success rates in both cases. But when combining the data, treatment B could appear superior because it was disproportionately used on easier-to-treat small stones. A doctor looking only at the aggregate data might choose the inferior treatment. This exact scenario occurred in real studies of kidney stone treatments in the 1980s, potentially affecting patient outcomes. The paradox also has significant implications for economic policy and business decisions. In the 1990s, economist Lawrence Summers, then at Harvard, identified a Simpson's paradox in wage gap studies. While women's wages were growing faster than men's within specific age and education groups, the overall wage gap appeared to be widening because more women were entering the workforce in lower-paying categories. Similarly, a company might see declining sales in every regional market, yet show overall growth if it's expanding into new markets, a phenomenon that could lead to disastrous strategic decisions if misinterpreted. In the age of big data and machine learning, Simpson's paradox has taken on new importance. Algorithmic models trained on aggregated data can learn completely wrong relationships if confounding variables aren't properly accounted for. For instance, a credit scoring model might paradoxically penalize a demographic group that actually has better repayment rates within every income bracket, simply because that group is overrepresented in lower income categories where default rates are higher. As predictive models increasingly influence everything from loan approvals to criminal sentencing, understanding and avoiding Simpson-type reversals becomes an ethical imperative. The paradox even appears in sports statistics. A baseball player might have a higher batting average than another player in both the first and second halves of a season, yet a lower average overall. This happens if the first player had more at-bats when pitching was strong, suppressing averages, and fewer when pitching was weak, another example of how weighting and sampling can distort apparent performance. Statisticians have developed several approaches to avoid being misled by Simpson's paradox. The most straightforward is stratification, breaking data into meaningful subgroups before analyzing relationships. Causal diagrams, developed by Judea Pearl and others, help identify which variables need to be controlled for to determine true causal relationships. Bayesian methods can explicitly model how different data-generating processes might combine to produce paradoxical results. In machine learning, techniques like propensity score matching attempt to create balanced comparison groups that prevent confounding. Philosophically, Simpson's paradox challenges our intuition about how parts relate to wholes. In everyday reasoning, we often assume that relationships that hold for subgroups must hold for combined groups, an assumption the paradox shows to be false. It serves as a powerful reminder that correlation does not imply causation, and that statistical conclusions depend critically on how data is structured and analyzed. As datasets grow larger and more complex in our increasingly quantified world, the risk of Simpson-type reversals grows accordingly. The paradox also has implications for scientific reproducibility. Two studies might reach opposite conclusions, both correct if they aggregate data differently. This was seen in early COVID-19 research, where treatment effectiveness appeared to vary drastically depending on how patient subgroups were combined. Such cases highlight why meta-analyses must carefully account for study heterogeneity rather than simply pooling results. Ultimately, Simpson's paradox is more than a statistical curiosity. It's a fundamental lesson in humility when interpreting data. It shows that the truth often lies not in surface-level patterns, but in the underlying structure of how variables interact. In an era where data-driven decision-making dominates everything from healthcare to public policy to business strategy, recognizing and accounting for this paradox can mean the difference between insight and error, between effective interventions and costly mistakes. The next time you see a striking statistic or trend, it's worth asking, what might this look like if broken down differently? Because as Simpson's paradox teaches us, the whole truth is rarely just the sum of its parts. The ancient Greek philosopher Zeno of Elea crafted a series of paradoxes that have challenged our understanding of motion, space, and time for over 2 millennia. Born around 490 BCE, Zeno was a disciple of Parmenides, who argued that reality is unchanging and that motion is an illusion. Zeno's paradoxes were designed to defend this radical view by demonstrating that common-sense notions of movement lead to logical absurdities. The most famous of these, the dichotomy paradox, poses a simple yet profound question. How can you ever reach your destination if you must first traverse half the distance, then half the remaining distance, and so on ad infinitum? At first glance, it appears that motion requires completing an infinite number of tasks in finite time, which seems impossible. The dichotomy paradox isn't merely about dividing space, it also implies a division of time. To move from point A to point B, you must first reach the midpoint, which takes some time. Then you must reach the next midpoint, which takes additional time, and so forth. If space and time are infinitely divisible, then completing the journey seems to require an infinite series of steps, suggesting you could never arrive anywhere. This paradox, along with others like the arrow paradox, which argues that at any instant, an arrow in flight is motionless, so how can it move? And Achilles and the tortoise, where the swift Achilles can never overtake a slower tortoise given a head start, strikes at the heart of our intuitive notions of continuity and change. For centuries, these paradoxes resisted complete resolution because Greek mathematics lacked the tools to handle infinite series rigorously. Aristotle attempted to refute Zeno by distinguishing between potential and actual infinity, arguing that while space is infinitely divisible in theory, we don't need to complete an actual infinity of steps to move. However, his solution was more philosophical than mathematical. The real breakthrough came with the development of calculus in the 17th century by Newton and Leibniz. Calculus provided the machinery to handle infinite processes through concepts like limits and convergent series. In modern terms, the dichotomy paradox is resolved by recognizing that an infinite series can sum to a finite value. The total distance covered in Zeno's scenario is the sum of the series 1, 2, ion, 1, 4, ion, 1, 8, ion, which converges to 1. Similarly, the time taken to complete these steps forms a convergent series, meaning the entire journey can be completed in finite time, despite involving infinitely many intervals. This mathematical resolution shows that motion doesn't require completing infinity in an impossible sense, but rather that infinite subdivisions can coherently describe finite phenomena. However, the paradoxes still raise deeper questions about the nature of space and time. Are they truly continuous, as classical physics assumes, or might there be a smallest, indivisible unit of space or time? Quantum mechanics hints at the latter. Planck length and Planck time are often interpreted as fundamental limits to how finely space and time can be divided. If space-time is discrete at some scale, Zeno's infinite subdivisions would break down, potentially offering a physical resolution to the paradox. Yet even this interpretation is speculative. Quantum gravity theories, like loop quantum gravity, propose discrete space-time, but no experimental evidence has confirmed it. Zeno's arrow paradox, meanwhile, touches on the nature of instantaneous velocity. If time is composed of indivisible instants and the arrow is motionless at each instant, how does motion arise? Modern physics addresses this through the concept of limits. Velocity isn't just about position at a single instant, but about the trend as time intervals shrink to zero. This idea, formalized in calculus, shows that motion can be understood as a property emerging from infinitesimal changes, not just static states. The philosophical implications of Zeno's paradoxes extend beyond mathematics. They force us to confront how we model reality. Do our descriptions, like continuous spacetime, correspond to how things truly are, or are they just useful approximations? In physics, the continuum model works extraordinarily well for most purposes, but at quantum scales, it may break down. Similarly, in mathematics, we can work with infinities rigorously, but whether nature actually contains infinities remains an open question. Zeno's paradoxes also influence the development of modern logic and the philosophy of language. They highlight how subtle misstatements about infinity or motion can lead to apparent contradictions. Analyzing these paradoxes helped refine definitions of concepts like limit, continuity, and instantaneous rate of change, which are foundational to much of modern science and engineering. In the 20th century, new variations of Zeno's ideas emerged in quantum physics. The quantum Zeno effect describes how a system can be frozen in its initial state by repeated observations, a bizarre echo of Zeno's argument that motion is illusory if closely scrutinized. This effect has been experimentally verified and even proposed as a method for error suppression in quantum computing. Ultimately, Zeno's paradoxes endure not because they are unsolved puzzles, but because they crystallize profound tensions between human intuition and the mathematical descriptions of reality. They remind us that concepts we take for granted, like movement from one place to another, are far stranger than they appear. The resolution through calculus doesn't entirely dissolve the mystery. It merely provides a consistent framework to work within. Whether space-time is continuous or discrete, whether infinities are actual or potential, these questions continue to drive research in physics, mathematics, and philosophy. Zeno's legacy is a testament to the power of simple, sharp questions to unravel hidden complexities. His paradoxes teach us that progress often comes not from dismissing apparent contradictions, but from digging deeper into them, revealing layers of structure in the universe that our ancestors could scarcely imagine. As we grapple with modern equivalents of Zeno's problems in quantum gravity and the foundations of mathematics, we are still walking the path he first pointed toward over 2,000 years ago. A path where every step forward reveals new questions, and every answer opens fresh paradoxes. The Ship of Theseus stands as one of philosophy's most enduring thought experiments, probing the fundamental nature of identity and continuity. Originating in ancient Greek philosophy and later popularized by Plutarch, the paradox asks whether an object that has had all of its components replaced remains fundamentally the same object. The scenario presents a ship belonging to the mythical hero Theseus. Over time, each plank of the ship is replaced as it wears out, until eventually none of the original material remains. The central question emerges: is this fully repaired vessel still the Ship of Theseus? The paradox deepens when considering what would happen if someone collected all the discarded original planks and reassembled them into a ship. Which version, if either, could claim to be the real Ship of Theseus? This deceptively simple question unravels into complex layers of metaphysical inquiry. At its core, the paradox challenges our intuitive notions of identity over time. We commonly speak of objects persisting through change. A car remains your car even after replacing its tires, battery, or even its engine. But the Ship of Theseus pushes this intuition to its limits by proposing complete material replacement. The paradox forces us to examine what actually constitutes sameness. Is it continuity of form, of material composition, or something more abstract like historical trajectory or functional organization? The philosophical responses to this paradox have branched into several major schools of thought. The essentialist position argues that identity is preserved through some unchanging core essence. For the Ship of Theseus, this might mean that as long as the ship's fundamental design or purpose remains unchanged, it maintains its identity despite material replacement. This view resonates with how we often treat objects in daily life. We consider a rebuilt classic car to be the same car if its original form and function are preserved, even if most parts are new. In contrast, the mereological essentialist view maintains that an object is strictly identical to its particular collection of parts. From this perspective, replacing any component creates a numerically different object. This leads to the conclusion that the Ship of Theseus ceases to be the same ship once any original plank is removed, making identity an all-or-nothing proposition that doesn't allow for gradual change. This interpretation, while logically consistent, conflicts with our everyday experience of objects persisting through minor modifications. The dominant contemporary approach comes from the psychological continuity theory of identity, most notably developed by John Locke. This view suggests that identity persists not through material continuity, but through the maintenance of organizational structure and causal connections over time. Applied to the Ship of Theseus, the ship remains the same because each new plank is integrated into the existing structure in a way that preserves the ship's functional and historical continuity. This perspective aligns well with modern biological understanding. Our bodies replace nearly all their cells every 7 years, yet we maintain a sense of continuous personal identity. Modern science has provided fascinating parallels that illuminate the Ship of Theseus paradox. In biology, the process of homeostasis demonstrates how organisms maintain their identity despite constant material turnover. The human body replaces about 330 billion cells per day, with different tissues regenerating at different rates. The stomach lining renews every few days, skin cells monthly, and even bones completely remodel themselves every decade. Yet despite this complete material turnover, the organism maintains functional and structural continuity. This biological Theseus's ship suggests that for complex systems, identity may reside more in patterns of organization than in specific material components. Neuroscience adds another layer of complexity to the paradox. The human brain undergoes constant synaptic reorganization, with neurons forming and breaking connections throughout our lives. While most neurons aren't replaced, with some notable exceptions in certain brain regions, their configurations and molecular components are in constant flux. This raises profound questions about personal identity. If our memories and personality persist despite this continuous remodeling, what does that imply about the nature of consciousness and selfhood? The paradox becomes even more intriguing when applied to artificial systems and digital information. Consider a computer file that undergoes numerous format conversions and platform migrations over decades. Is it the same file if all its binary representations have changed but its informational content remains intact? This digital parallel to the Ship of Theseus becomes increasingly relevant in our age of cloud computing and distributed systems, where data persistence often has little connection to physical storage media. Quantum physics introduces another dimension to the discussion through the phenomenon of quantum identity. Elementary particles of the same type, like electrons, are fundamentally indistinguishable. They have no individual identity beyond their quantum state. This suggests that at the most fundamental level, material objects might not have the kind of persistent identity we intuitively ascribe to them. The Ship of Theseus, when examined at quantum scales, becomes a constantly fluctuating collection of indistinguishable particles, challenging traditional notions of objecthood. The paradox also has practical implications for fields like artifact conservation, software engineering, and even legal definitions of property. Museums frequently face Theseus-like dilemmas when restoring artifacts. How much original material must remain for an object to maintain its historical authenticity? In software systems, the Theseus release problem occurs when considering whether a system that has been completely rewritten can be considered the same product. Legal systems grapple with similar questions when determining ownership of heavily modified property or intellectual property that has evolved over time. The reassembly version of the paradox, where all original components are gathered to reconstruct a ship, presents an even more challenging scenario. This forces us to consider whether identity can branch or whether historical continuity takes precedence over material composition. Some philosophers argue that neither ship can claim to be the original, while others propose that identity follows the path of continuous maintenance rather than reassembly. This aspect of the paradox has particular relevance for emerging technologies like 3D printing and molecular manufacturing, where objects could theoretically be disassembled and reassembled at will. Cognitive science research suggests that our perception of object identity may be more about mental constructs than physical reality. Studies show that people's judgments about whether something is the same object after changes depend heavily on contextual cues and narrative framing. This psychological dimension explains why we can simultaneously recognize both versions in the Ship of Theseus paradox. As having claims to authenticity, our brains are comfortable maintaining multiple, sometimes contradictory, identity assignments depending on the frame of reference. The Ship of Theseus continues to resonate because it encapsulates fundamental questions about the nature of reality and our place in it. As technology advances into areas like nanotechnology, artificial intelligence, and quantum computing, the paradox becomes less abstract and more practically relevant. The decisions we make about what constitutes identity in machines, digital entities, and even potentially uploaded consciousness may hinge on how we ultimately resolve this ancient thought experiment. Perhaps most importantly, the Ship of Theseus teaches us that identity is not a simple binary property, but a complex interplay of material, formal, functional, and historical factors. In a universe of constant change, the paradox reminds us that persistence is not about remaining unchanged, but about maintaining coherence through transformation. As we face new versions of this ancient dilemma in biotechnology, artificial intelligence, and beyond, the Ship of Theseus continues to sail through our philosophical waters, challenging us to rethink what it means for anything or anyone to remain the same over time. Now, as we settle back into the quiet, let's remember, some questions don't have clear answers and maybe they never will. But in their uncertainty lies something beautiful, a sense of wonder, a feeling that we're part of something much larger and more mysterious than we can grasp. Let these thoughts be like stars fading into the night sky, distant, peaceful, and still unsolved. Sleep well.